All right, so today we're going to talk about a new topic called eigenvectors, eigenvalues, and diagonalization. So the rough idea of what we want to do, and this is going to take several sessions, but the rough idea is we want to boil down every matrix to just a few numbers. And by the few numbers, it's the numbers that it acts like. So here's a very concrete example to keep in mind. And we're going to run with this example much later. So this matrix, this is the 2 by 2 0 matrix. In this sense, this acts like 0. So we want to say it has the eigenvalue of 0. And so in some sense, one of the connections we want you to make is, right, it acts like 0. We know that you can't divide by 0. So for example, 1 over 0 exists only if x is not equal to 0. In much the same way, we want to say something like a to the minus 1, which is the same thing as dividing by a in the matrix language, exists only if a has no eigenvalue of 0. So in some sense, the eigenvalues are going to describe what the matrix acts like. And that's really the main idea of eigenvalues and eigenvectors. So let's go ahead and that's just to give you an overall picture of where we're going and why we're doing this. Right? That's not at all a technical, precise definition. So let's give a very precise definition. So what we're going to do is we're going to call an eigenvalue and eigenvectors. So if we have a vector v that equals lambda v, then we're going to call this v right here. This vector v, this is v is an eigenvector. And this lambda here is an eigenvalue. So this is what it means to be an eigenvector and eigenvalue. One important thing to keep in mind is that the context of eigenvalues and eigenvectors require a matrix. So eigenvector and eigenvalue are properties related to a matrix. So you can't call something an eigenvalue or an eigenvector unless there's some matrix you're talking about. In much the same way, you can't call a single vector independent or dependent unless it's the context of a set. And that's in that case, it could be the set of a single vector, but you can't just say some vectors are independent and other ones aren't without having the context of a group of vectors. And in much the same way, you can't talk about eigenvectors and eigenvalues without the context of an actual matrix A. So let's just give an example of what this looks like. So here's an example. So we're going to consider the matrix 1, 1, 1, 1. And I'm just going to tell you that the vector 1, 1 is an eigenvector with eigenvalue 2. And 1 minus 1 is an eigenvector with eigenvalue 0. So this in some sense says that the matrix 1, 1, 1, 1 acts like the number 2 in some ways and the number 0 in other ways. Right? And we're going to spend further sessions figuring out how to come up with these numbers, right? These numbers, I'm just telling you, these are fact, and we're going to check them in a second. So don't be too anxious about where these numbers came from, but let's go ahead and check this. So we can check this one right here. So we're going to check this fact. So if we multiply 1, 1, 1, 1 by the vector 1, 1, we're going to get 2, 2, which is equal to 2 times what we started with. So this eigenvalue is just a multiple that it multiplies by. So one way of thinking of an eigenvalue is it's the number that the matrix stretches a particular vector by. So if we start with 1, 1 and multiply by A, we're going to get the same vector on the out back times a factor. In this case, it's 2. But it's only a factor for that very specific direction. And likewise, we can check this other eigenvalue, an eigenvector pair. So if we get that one, we'll get 0, 0, which is equal to 0 times 1 minus 1. So again, that's where that 0 comes in. If we multiply 1 minus 1 by the matrix, we'll get 0 times what we started with. To kind of put this in pictures, let's go ahead and put this into a before and after graph. So if we start with a before and after graph, we're going to start with a few vectors. I'm going to start with these vectors right here. And we're going to take the transformation 1, 1, 1, 1, and we're going to see where these vectors end up. And this is going to be a good segue to our next point. So let's just figure out where these go. So this red one's going to go to, this is 1, 0. When we multiply it by the matrix, we get to 1, 1. That orange vector, when we multiply it by the matrix, that orange vector is going to be 0.7, 0.7. Actually, let's just, for sake of simplicity, let's just keep it to, let's make this 1, 1 here. Let's make it a box instead. So it's going to be, this is then going to go to 2, 2. I'm just going to go around here. That one's going to go to 1, 1 as well. This blue one, which we're going to call minus 1, 1, that's going to go, if we multiply it by the matrix, we're going to get 0, 0. And then finally, this other vector, minus 1, minus 1, will get stretched out to minus 2, minus 2. All right, so this is kind of the picture of what this looks like. Right, but what I want to emphasize is what it looks like for the eigenvectors. The eigenvectors are going to be in the exact same direction as they were. So you'll notice that that orange vector, that's an eigenvector because they're exactly in the same direction. They could be flipped or stretched, but they're otherwise in the same direction. And you'll notice that that stretch is by a factor of 2. And also for the eigenvector of 0, you'll notice that we had this one. That's an eigenvector of 0 because it's multiplied by 0 right when it gets there. And there's one other eigenvector hidden in here, and that's this purple vector. This purple vector right here happens to be in the same direction as 1, 1, and it too also gets stretched by a factor of 2, 2. All right, so this leads us to 2 important points. The first important point is that if V is an eigenvector, then so is any multiple of V. And that's illustrated right here in this picture, right? The purple vector minus 1 stretched by the same factor as 1, 1, which we told you was an eigenvector, right? And so similarly, we also have that if we take this other vector here, say 1, 1, the one I told you was originally an eigenvector, that one's also going to get squashed right to the origin too. That's also going to be an eigenvector as well. So any multiple of a vector is also, any multiple of an eigenvector is still an eigenvector. Okay. The other important thing that we're going to make it kind of a big deal about is you'll notice here that we started with kind of this 2-dimensional box, and they got squashed all the way down to a line. And so we know from our experience that we know that because of the squashing, that this matrix 1, 1, 1, 1 is not invertible. So the other important point that we're going to make a big deal about is that if A has an eigenvector of eigenvalue of 0, then A is not invertible. Right, so this is an important point. We can relate eigenvectors to what we know. So now this tells us a lot of things, that the eigenvectors and eigenvalues are related to all the other things we've previously done, to kernels and images, to pivot positions, to determinants. So you can write off a whole list of things. So for example, we can write off that A has eigenvalue 0 is the same thing as the determinant of A being 0, which is the same thing as the columns of A are linearly dependent, which is the same thing as A is not invertible, which is the same thing as the kernel of A is not just 0, 0, or the 0 vector, right? And this list goes on, but this is kind of why we care about eigenvalues and eigenvectors, is it fits into this nice little picture about whether or not a matrix is invertible, but also quantifies this, right? So in some sense, if you want to go deeper into matrices, you want to also ask the question, what does it mean to almost be invertible or almost not be invertible? Well, if you have an eigenvalue close to 0, that means you're getting close to not being invertible. So it kind of quantifies how close you are to be invertible, besides it being a binary question. But that's beyond the scope of what we're going to do. Okay, so what are some other cool things we can do with eigenvalues and eigenvectors? And that's going to bring us to diagonalization. So diagonalization means that we want to ask the question, so we want to ask, is A similar to a diagonal matrix? So that's kind of our question. And the answer here is we can do this. This is for most matrices, the answer is yes. So as a warning, it's not always going to be yes, but for almost all matrices, we can actually make it similar to a diagonal matrix. So just as a reminder, what does similar mean? Similar means that we want to write A as S D S inverse, where this D right here is going to be a diagonal matrix. And as it turns out, which I'm going to show in a second, this matrix S here, this is going to be a matrix of the eigenvectors. And the diagonal matrix has corresponding eigenvalues. So this is, in some reason, why we care a lot about eigenvalues and eigenvectors, is that it lets us decompose a matrix in a very simple way, where we can, instead of thinking of this generic matrix A, we can instead think about it as the diagonal matrix D. And every diagonal matrix is just a stretch in certain directions. So instead of thinking of matrix A as doing these complicated things in all sorts of different directions, what we're really doing is we're boiling down the matrix into which directions have that perfect stretch. So just like up here, we have this orange vector has this very perfect stretch by a factor of 2, and what directions those are. So if we can detail those, we can recover A and describe A in perhaps a more succinct way. So that's really what we're doing here. Instead of describing A as just a box of numbers, we're saying, okay, stretch it in very particular directions. All right, so let's do this as an example first, and then we can talk about, as we do the example, why this breakdown works and how you should think about it. All right, so here's the example. So suppose we have the matrix 1, 2, 2, minus 2. And I'm going to tell you that this has eigenvectors -1 and 2, and 2, 1, with eigenvalues -3 and 2, respectively. So just for emphasis, it's important that eigenvalues and eigenvectors come together in a context. So you're not allowed to just say these are the eigenvalues and these are the eigenvectors. You have to assign them to one another. So those are the eigenvector eigenvalue pairs that happen to coincide with this matrix. Just for emphasis, we're going to figure out later how to come up with these numbers and vectors. But for right now, let's just take these eigenvectors and eigenvalues just at face value. And the question we want to answer is how to write this matrix as A equals SDS inverse. And or put another way, we want to, how do you diagonalize this matrix? How do we diagonalize it? So diagonalizing just means make it similar to a diagonal matrix. And that's going to mean finding or using the corresponding eigenvalues and eigenvectors. All right, so it turns out we've actually done a very similar problem to this. So let's just talk about why this is similar to another problem with this. So what is this really saying in other languages or other phrases that we know? So this eigenvalue eigenvector pair, this just means that A stretches 1 minus 2 by a factor of 3. A factor of -3. So maybe we should say stretch. So this factor of -3 really says it's going to flip and stretch. Right. And also A is going to stretch this other eigenvector eigenvalue pair. Means that A stretches the vector 2, 1 by a factor of 2. So we kind of already have seen this problem when we did similar matrices. So let's just give a recap of how this really works. So what's going to happen is if we wanted to take the matrix A and multiply it by xy, right? You could just, in this case, we know what A is. We could just multiply it out. But instead what we're going to do is we're instead going to write xy, and we're going to write it as some multiple of -1, 1 plus some multiple of 2, 1. And then we're going to multiply that by A. So the first thing we want to do is we're going to change the basis to do that. And then what we can do is now we're going to apply A. But to apply A, what we're going to do is we're going to kind of distribute A into here. And we can apply A to those vectors. Now, the key thing here, and the thing that's hard to wrap your head around, why aren't we just going to multiply A using the matrix multiplication? Why are we doing this? Is because in some ways, it's easier, especially if you don't know what the exact matrix is, it's easier to ask the question, where does A just stretch the vector? And that's what we're doing here. So we're going to convert the bases over to the eigenvalues and eigenvectors. And then we're going to apply A. So this is just applying the simple stretch. So if we apply the simple stretch, this is just A times this, in this case, this first one's -3 because the eigenvalue for this first vector is -3. We don't even, I don't even know what A is on the screen right now, right? I have no I forget what A was. All I know is it's going to stretch this vector by a factor of 3. And likewise, it's going to stretch this other vector by a factor of 2. But we forgot this vector. And then we're going to add them up and apply it. And then we add them up and apply it back to the standard basis. All right, so now if you remember when we did similar matrices, each of these transformations that we did, we changed the basis, we applied the simple stretch, and then we moved it back to the standard basis, actually is the process of a similar transformation. So this first transformation, that is change the basis away from the standard XY basis. So that's going to be S inverse. So that this first one is just S inverse. When we apply the transformation here, right, when we did the stretching, this is just the same thing as applying D, and then applying it back to the standard basis, right? We're moving it from kind of the coefficients of -1, 2, 2, 1 to the standard basis. That's just applying S. So altogether, what do we have? We have that A is equal to, we applied S inverse first, and then D, and then S. And this S is just going to be the standard, not the standard, the eigenvectors that we have, right? The basis we're using is the eigenvectors as the basis. The amount of stretching that we did was just -3 in this direction and 2 in this direction. So that's going to be our stretching. And then lastly, the S, to move it over here, we have S inverse. So it's just the S matrix inverted. And I still have forgotten what the matrix actually is, but we can come up with what it is if we were to multiply all this out. And we can compute the inverse of this, which happens to be -1/5, 2/5, 2/5, and 1/5. You can get that using the formula 1 over -1 minus 4. That's the determinant times swap A and D and subtract those. And if you simplify all that, you'll get the inverse. So this right here is SDS inverse. And this should be equal to the matrix that we started with. And the matrix we started with was, see, I forgot what it was. It was just 1 minus 2. And what was it again? It was 1, 2, 2 minus 2. All right, so we can break up 1, 2, 2 minus 2 into these parts if we know exactly its eigenvalues and eigenvectors. All right, so let's just finish with a few fun facts and notes. So a couple things that you'll notice right here, that these are the eigenvalues, eigenvectors rather, and these are the corresponding eigenvalues. So given the context of this question, right, we kind of talked through it a lot, right? But once you know the eigenvectors and eigenvalues, I mean, this is just the thinking about why it actually works and what we're doing and why it's not just magic. But at the end of the day, this SDS inverse is just encoding the eigenvectors and eigenvalues in this way. You could jump down to here once you figure out what's really going on. Right, so this is just where the eigenvectors and eigenvalues go. It's important to put these in the same order and have them correspondingly. You can change the order of the eigenvalues and eigenvectors as long as they're consistent, as long as the first eigenvector is listed with the first eigenvalue, and so on and so forth. So the order matters. So this is one warning. Let's put this in red. So at least the correspondence. Right, so that's one thing that's important. So another thing that's important, this is not so much a thing, But keep in mind, one of the first fun facts that we did was that any eigenvector and any eigenvalue, so any eigenvector can be scaled, right? So 1, 2 is an eigenvector. Minus 1, 2 is an eigenvector. So that means that minus 2, 4 is also an eigenvector with the same eigenvalue. So what this really means is that this SDS inverse is not unique. So what this says is this SDS inverse is not unique. We didn't have to use specifically these eigenvectors, nothing special about these eigenvectors. We could have used any multiple of minus 1, 2, and 2, 1 when we did SDS inverse. The only thing is whatever we use for S has to be the same what we use for S inverse. We have to take the inverse of S. So when you scale minus 1, 2 up, that's going to be taken care of when you find the inverse of S. Right. So this is just a kind of a quick overview of what diagonalization of eigenvalues and eigenvectors are. A lot of the problems are about getting your feet wet, about understanding some of the kind of maybe straightforward but not completely obvious properties of eigenvalues and eigenvectors. And some of them are trying to get to the essence about why we really care about them. What are some other fun things that are going to happen with eigenvalues and eigenvectors?